Okay, so this video will be about making an emulator, or more technically, an interpreter for the CHIP-8 language. So CHIP-8 was originally an interpreted language made for writing video games during the 1980s. So the idea was you could write your game in the CHIP-8 language, which as we'll see is basically a list of opcodes, and people would write different interpreters for this language for different systems. And so your one game could run on several different systems without you having to write your game specifically for every console that you wanted to play on. So this is a very good project for kind of beginning in emulation and also practicing a bit of kind of computer architecture. And so the reason it's such a good project is because you have very few opcodes to implement and a very simple virtual machine. And so compared to something like the NES, where you may have several different mappers to deal with and different units, here you really only have the RAM, the stack for function calls, the screen and the input from the keyboard, and some timers, and of course the registers you use for the opcodes. And that's really every single component in the system. So it's very simple to start with, and you can implement it really in about a weekend, maybe two. So I'd recommend it's a great project if you want to practice emulation, and you can run all these ROMs that already exist to kind of see just how well your interpreter works. So let's have a look at the technical details of the CHIP-8 system. So if you do want to write your own interpreter, I really recommend this CalGod's CHIP-8 technical reference. So you can see the URL for this below, and I'll put this in the video description. And well, let's see what he says about the CHIP-8. So as you can see, he mentions that it was used for kind of many different consoles, so you could deploy one game across several consoles. And nowadays it's mostly used as kind of a beginner's project for kind of emulation, despite not really being an emulator, because you're not emulating kind of what were real opcodes, but actually this kind of interpreted bytecode. So let's look at the actual technical specifications of the system. So you can see here the memory of the CHIP-8 has 4 kilobytes of RAM, so 4096 bytes from 0x00 to 0xFFF. And you can see he's also produced this excellent ASCII diagram of the memory map. And so down at the bottom we have 0x000 to 0x1FF is reserved for the interpreter. In practice, the font is actually stored here, so that is the sprites for all of the characters from 0 to F, which games can then call on to draw them on the screen. And then at 0x200, we copy the ROM. So byte by byte, we copy the entire ROM beginning at 0x200, and that ROM can use the rest of the memory as it desires. Maybe the ROM is very large and it can put data there too, or it can write there and copy data there and do whatever it wants. So the system itself has several registers. So the kind of the most important, the most used in practice are the V registers, and these are 8-bit registers. So there are 16 of them from V0 to VF. And, well, but VF itself is a special register. So as mentioned here, VF is used as a flag in certain instructions. So for example, if you have an instruction that might cause an overflow. So for example, here we're dealing with 8-bit registers. If you were to add two large numbers together, say 200 and 200, that would overflow the 8 bits. And that will then cause this flag to be set. So even though it will overflow, at least you know that it overflowed, and then you can handle that in the ROM. And so this is one example where ROMs shouldn't use this register for other purposes, but some might do. There's no kind of rules or checks to stop them from using that in any other way. And this can be an issue when you're working with some ROMs that might have weird behavior. So finally, we also have a 16-bit register called the I register, which is mostly used for jump operations because it can hold an entire memory address in 16 bits. But you could also use it for other purposes too. And then we have two 8-bit registers for delay and sound timers. So these work a bit differently, that when they're set to above 0, they decrement at a rate of 60 hertz. And so that means you need to keep track of that time. So that's 60 hertz in real time. So you need to keep track of that inside of your interpreter. And the sound timer, every kind of frame that it's above 0 should produce a continuous beep, which then stops when it reaches 0. The delay timer, on the other hand, can be polled by certain opcodes, and so it's more used for kind of timing stuff between. So like basically a way of like handling timing within your ROM. So if you wanted to have a timer in your game, this allows you to do that. So finally, we have kind of some registers internal to the interpreter. So we need a program counter, which should be 16-bit, basically to keep track of which opcode we're on. So when we jump around, we know where we are. And the stack pointer, which can be 8 bits, which points to where we are on the stack. So the stack, as mentioned here, can be up to 16-bit values. And they're basically, it's used to store addresses. So when you do a function call, you put where you were on the stack, and then when you finish the function, you pop from the stack and jump back to where you were. So a lot of ROMs will do this as a way of implementing functions, and we need to be able to handle that too. So let's have a look at the rest of the system before we have a look at the kind of implementation. So the keyboard has this weird layout. It's like a hexadecimal layout. So in my case, I actually mapped this to 1, 2, 3, 4 on the top, QWER, ASDF, ZX, CV. And this makes it mostly playable for most ROMs. It's still a bit awkward. It's not quite similar to what the original keyboard was. I had these as kind of buttons directly on top of each other as shown here, but it's close enough that it's usable. So the display is a 64 by 32 pixel black and white display. So, I mean, that's a very small number of pixels. So in practice, we'll want to make these pixels larger when we draw it on the screen. And notice that's 32 rows and 64 columns. So in my case, I actually implemented this with a bitmap. So those aren't, so it's not using a byte for every one, but rather kind of a pixel is 1 bit as part of a byte, which we'll see in the implementation. So finally, we also have here the font that, as mentioned previously, is stored at those memory addresses. And this is basically so that the games can write each of these characters to the screen, and they don't need to define every single ROM doesn't need to define its own font, although they're free to define other sprites inside their ROM. So, and finally, as mentioned previously about the timers. So, yeah, the sound ideally should be constant, but this can be a bit difficult to do. So in my case, I just made it as the system speaker, so it's not exactly constant, but it's close enough. So finally, we have here the opcodes. But before we look at the opcodes, let's look a bit at the implementation of the virtual machine. So here I have the code from my repository, CHIP-8go, and we can have a look at the source code here. So I've split out the source code into several different blocks. So chip8.go is just handling the command line arguments to launch the interpreter. Chip8 test has the majority of the unit tests for the virtual machine and interacting with the interpreter. SDL has the SDL code for creating the window and some code for drawing the window. That is then exported via an interface to the virtual machine. SDL input has the SDL code for interacting with the keyboard. That again defines a few functions that are exported as an interface to the virtual machine. This is so that if I wanted to, I could re-implement another interface with cursors, for example, to run it in the command line directly. And finally, it has some utilities and utility functions that have tests as well. And then the virtual machine itself, which is the majority of the code. So this is a struct for the virtual machine. And you can see here we have basically an implementation of everything that was just described. So our V registers are implemented as a kind of 16-length array of 8-bit integers. So those are all 8-bit values, so 1 byte, and there are 16 of them exactly as described. We have our 4 kilobytes of memory. Again, each byte is separate, so as an 8-bit unsigned integer, and that gives us all of our memory, which we can write to. And remember, we also have to copy the ROM there and prepare that, which I'll show in a moment. Then we have the screen, which is actually indexed. So the row is indexed first, and then the column. But note, should be kind of 64 by 32. So we have 32 rows, and we should have 64 columns. But we have 8. And the reason is that this is implemented in bytes. So actually, each bit of the byte is a pixel. So it's a bitmap. And to operate over that, we can use bitwise operations to kind of manipulate each pixel itself. Then we have the two timers, again, implemented as 8-bit values. The stack, which as mentioned needs to be 16-bit due to the fact that it holds memory addresses which can exceed 8 bits. And that can be up to 16 in size, and in practice I don't think any ROMs reach this. And then finally I have some values that I've created as options for the interpreter, so whether to wrap the X and whether to wrap Y. So for that is if you exceed, for example, if you exceed 64 columns, if you try and write to 65, does that wrap around and write to the first column, or does it throw an error, or does it fail silently? What should it do? So I actually have all of those operations for why this is a string. Ideally this would be an enum, but at the moment it's a string, and so to handle all those cases, so it can error, it can fail silently, or it can wrap around, and the same for the Y. And I've actually found ROMs that expect both of these to wrap. Far fewer in the case of the Y, of wrapping rows, but it can still happen. So then the clock speed is also a variable. So this is because the clock speed in CHIP-8 isn't actually standardized. So I put a value of about 1000 Hertz, works okay, but it's a bit awkward that this isn't standard. So it can vary between the ROMs. So you find some ROMs you run at that speed will run incredibly fast, whereas some will require that speed to run an acceptable rate. So it's a bit awkward that this isn't standard, but it's something you have to deal with. Finally, the time speed should always be 60 Hertz. This is standardized, and I just made it an option for testing, so I could do different tests and check the times are working okay. And finally, have the screen buffer. So the screen buffer is how many screens do I want to hold as a buffer, which I then kind of OR together to stop flickering. So the reason this can happen is because some ROMs, the way they draw, will be to kind of draw to the screen and then delete what they drew and then redraw. So for example, if you're drawing the paddle in Pong, you can first delete the paddle you drew on the previous frame, and then you could have one frame without any paddle, and then you draw the new one. But the problem is, depending on how this runs and what's going on, this can cause flickering because the screen could redraw before you've redrawn the new one. And so if this happens, you end up with flickering, and this is quite a problem in a few ROMs. And so basically to stop this flickering, which is very distracting, I just added this buffer which doesn't kind of a bitwise OR between the screens. And I mean, it's not always necessary, but it's nice to have the option there. So, I mean, let's quickly have a look at this. So here's where we set the font in Initialize font. So we literally have the values as given. So for example, this is 0, and this is literally the values in pixels. So remember, each bit is a pixel, so F has all the bits set, and then no bit set. And so here, like F999F corresponds to what a 0 would look like if you were to write that out. And so this is the case for all of these, all of them implemented, basically read from the documentation. And those are stored at those addresses so that ROMs can use them without having to define it themselves. Then we also load the ROM to the memory starting at OX200, and then we just copy every single byte of the ROM. And then when we go to actually use this, we set some flags. So we set that we're not drawing, and we set the options as before. And then this basically gets the whole machine ready to run. And then we can start passing opcodes in a loop, and that basically runs the ROMs. So let's have a look at one of the ROMs in detail. So before we look at the opcodes, we can actually look at a ROM itself. So the ROM is just these opcodes in binary. So here they are in big engine form, luckily. So we don't need to do anything special with XXD. And so here it is in hexadecimal. So we can see the first opcode. So each opcode is 2 bytes. And the first opcode in this case is 00E0. And now we can look at our list of opcodes and say, okay, what does this do? And we see here 00E0 clears the display. So this should set all the values on the screen to 0 and then redraw the screen. So that's the first operation. So we would look at this, okay, run that and move on to the next one. So the next one is 6300, and we can have a look at what this does. And this is load VX bytes. So it sets the XV register to the byte given. So in this case, we're setting V3, so the 4th register in V, to the byte 00. And then we'd move on to the next opcode and so on. Basically, we loop through all the opcodes, kind of handling these cases. and that runs. So you can see here, for example, this is setting some memory, this is setting some memory again because it's starting with a 6, this as well, and now this one is doing something different. So free xkk skips an x instruction if vx is equal to kk. So we can see we just set the 5th register to be EE with this opcode, and here we're now checking did that set correctly. So this ROM is actually a test ROM, so it's designed to test a lot of opcodes and then write something to the screen if they fail. And so this is actually testing this opcode here, like is this implemented correctly? And if it is, it will skip this jump. So if we look here, 1 and an N is actually a jump operation, so it's jumping to 310. And so if it's implemented correctly, it will skip, and if not, it won't skip, and then it will write an error to the screen. Now, you may wonder, okay, how is this jumping to 310? Because if we look at down here, our ROM doesn't go up to 310 in length. And here we have to remember that in the memory map, we're copying this to OX200. And so this value here that it's actually jumping to would be 110, which is here. And then it would continue here to actually draw something to the screen where the D opcode is drawing. And so that's one thing you have to remember if you want to kind of debug ROMs, is to bear that in mind as well, that you are copying it. And so you can actually look at the details here. So this is a test ROM by bestcoder, and you can see here are the different types of errors. So it checks kind of all these opcodes for you. And again, this ROM is very useful when you're implementing these opcodes to make sure have you implemented them correctly, aside from writing your own unit tests as well. So let's go back here. So if we go down here, we should find, so here we have the implementation of all these opcodes. So we can see, for example, here's the implementation of the jump opcode, and first of all we extract kind of the address using the bitwise operation to get only the part we're interested in. So this like mask of only these 3 parts here. So kind of the second byte and also the lower part of the first byte. And then we want to check, okay, is this within the range of our memory? And if not, we want to fail and print that out. So, if we've made a mistake somewhere in our interpreter, we immediately know if there's an error here. And if not, the program counter here, PC, will be set to this value, and that will then cause it to jump. Because if we go back up to the top of this loop, we can see what we're actually operating on is the opcode itself, which is set here with from PC, so from the program counter. So, and you can see here, so here is that thing. Remember the opcode itself is 2 bytes, so we actually need to combine these 2 bytes. So here you can see I'm shifting the first byte to the left, and then kind of ORing it with the second byte to make one big 16-bit value that has the entire opcode, just to make it a bit easier to work with rather than having 2 separate values when you sometimes need, like as we just saw in that example, you need kind of the first, like the least significant part of the first byte as well. So hopefully that kind of explains how you'd implement all of these, kind of handling all of these opcodes. So one other thing we can look at here is also some of the SDL side of things. So here is the SDL code for dealing with the screen. So basically I create a window and I allow you to set the foreground and background. The important thing here is we have to have a scaling factor, because otherwise it's a very small number of pixels, and so we might want to make each pixel be, actually be 8 pixels in each direction, just so you can actually see it on a modern display. And so here I can set the scaling factor to whatever I want, and that allows you to kind of change the size of the window. So the screen is quite simple, and the keyboard is also quite simple. So if you have a look here, we can see, but here is the kind of initial configuration for the keyboard, but I actually read from an ini file, so this can be overridden. So for example, here I have pause to be the space key, but you could modify the ini file and write whatever you want. This was a bit complicated to get it to work because of the way SDL uses scan codes in different places, so we actually need to convert these to their scan codes and then use that in the code itself. So that's a good one. I mean, for the most part, this was incredibly simple. Given it was the first project that I've written in Go and the first real project using SDL as well, it worked very well. There was no kind of major issue here. So let's just have a look at the rest of the code here. So finally, we can have a quick look at the unit test as well. So here I've basically written unit tests for every single opcode. And I recommend doing this as you implement them. So you implement an opcode, you implement the unit test, you get the unit test to pass, and then when you've implemented enough of them, you can run something like this test ROM or some other ROMs to check that everything's working correctly. And so here, for example, is testing the jump. And so we load it with this. So we load, okay, OX1310, so we'd want to jump to 310. And we run this. And then we want to compare. So first of all, we check that we didn't write to the I register. And then we want to check that we correctly set the program counter. So that the program count was set to 310. So basically, we're checking the state of the virtual machine after processing this opcode. And yeah, ideally you should do this for all of them so that you know you've implemented them correctly. So that's kind of the main part of the implementation. You can see how you'd implement it, how you deal with a loop, and how you should handle kind of input and the screen. So finally, let's look at the repository itself. So this is actually on GitHub. So you can see this here. And I also added the ROMs here and some documentation. Now, there are a few issues that I had during implementation. So I'll just go through some of these now. So one issue I had was with SDL. So the rect constructor in SDL, I thought for a long time that it took kind of two sets of coordinates, the upper left and bottom right coordinate, but actually it takes the upper left point and the width and height of the rectangle. And since these all have the same types, you kind of get no error. It's just that you're drawing very strange rectangles to the screen. And so this took a while to work out what was going on. I actually eventually found it by using govet, which is a linter for Go. And in this case, it forced you to name the parameters, so it printed out the parameter names, and then it was very clear what the error was. So I really recommend using a linter in whatever language you choose to use, as it helps catch small errors like this that can otherwise take up a lot of time. So I had another issue with the FX29 opcode. So this opcode gives you the memory address for the sprite, but it doesn't give you the memory address for the sprite of the value you give here, which can be 0 to F. But it actually gives you the memory address of the sprite for the value that you give here in VX. So for example, if you give 0, it checks the V0 register. That will have some value, and then it gives you the memory address for the sprite of that value, not of the value you give in the opcode. And this is a really tricky issue, and the problem is, again, you won't get any errors if you do this wrong. All you'll get is that you'll draw the wrong sprites to the screen, and it can be incredibly difficult to work out. So this actually caused a lot of issues that many things wouldn't use this opcode, but just in some ROMs, I kept drawing the wrong thing to the screen, and eventually I worked it out. But for a long time, for example, the score in Tetris wouldn't work, and this was the reason. So I also added screen buffering, as I discussed previously. So basically, this is to avoid flickering in ROMs where they clear the sprite and redraw, because there can be kind of a frame before it redraws. And yeah, so basically this kind of does a bitwise OR between the two screens, or two or more screens, and then kind of carries on. So this is quite useful. By default, I don't use it, but it's useful to have the option for certain ROMs, otherwise it wouldn't work. You also need to handle screen wrapping, especially in the X direction. So some ROMs will depend on it, both in X and Y. So you need to make sure you can kind of handle drawing off screen, and or at least have the option to make it error out in certain cases, depending on what you want to do. So there's also this draw collision flag. So here I had one issue where the collision flag should be set if any row of the sprite results in a collision, and I had a bug where I was basically only checking the last row. And again, because of the types, you won't get a type error or anything here. So you really need a very good unit tester to set this. So try and write unit tests to cover every possible collision case, so you know that this is working. Finally, there's a few ROMs with bugs in them themselves. So one thing you'll see quite frequently is collision issues, and this is actually an issue in the ROMs. So this isn't just an issue in the interpreter, but can actually be issues in the ROM code itself. And also note that some ROMs require different clock speeds and so on. As mentioned, that's why these should be options to the interpreter. Finally, I had one issue with STL threads on OS X, which meant I had to refactor some of the unit tests, because I wanted to test parts of the code that were also using STL, and this was a bit awkward. In the end, I got it to work with refactoring some of the code. But I think this may have been an OS X specific issue. So that covers kind of all of the issues I had. So let's finally look at some of the ROMs in practice. So here we are. Let me check our games. We can find Tetris, for example. And here we can move the parts around. It's a bit awkward with the keys. And then kind of hope to score. And as you score, it will update up to the top here with the score you've got. So that's just when you see the frame rate works very well, and overall this works really well. The controls are good, and yeah, this could be, this is playable. So let's look at another example here. So this is Breakout, and this actually uses the speaker. So maybe you can hear my PC speaker beeping, and so this actually uses the audio also when you die. And this also works quite well. Again, the frame rate is good. There's not too much flickering, and it's very playable. So hopefully these examples show you kind of what you can do with a CHIP-8 interpreter, and I hope you're also inspired to write your own. I think it's a very good project for learning the very basics of emulation and kind of computer architecture as well, if you want to go more into that. I also very much recommend doing the NAND to Tetris course if you are interested in both emulation and computer architecture, and I'll put a link to that in the description too. Finally, I'll also add some links to resources if you wanted to write a NES or Game Boy emulator, which are also very common. But bear in mind that both of those are kind of much more detailed in terms of both the separate components of the system and also the way different ROMs use those components. So for example, if you want to write a cycle-accurate NES emulator, then that's probably about a year-long project compared to writing something simple like this. So hopefully this has been useful, and hopefully you're also inspired to write your own emulator. So thanks for watching, and please write any comments if you have any questions, or if you choose to write your own emulator. And as always, please like the video if you want more content like this, and subscribe.